During the opening, I said this was our 8th edition of the conference. Now, there has been a single person having a talk in every edition of the conference. And this is Joaquín. So he is a long-time contributor to Boost. And for me, an expert in many things, including data structures. So Joaquín is going to talk today about hashing.
Perfect hashing.
Perfect.
Perfect hashing.
It's important to be perfect. So I leave you with Joaquín. Joaquín, thank you very much for contributing again to the conference and to the C++ community. Thank you.
Thank you, Mr. Daniel. We're going to be talking about perfect hashing. First of all, how many of you know how a regular hash table works? Yeah, most everybody. So you have a number of elements that want to insert into the table, and a hash function that maps each element into a hash value, typically a large integer like 64 bits wide, something like that. Then somehow you project or reduce those hash values into indices of a so-called bucket array. All right? The number of elements divided by the number of buckets arrays, we call it the load factor. And that's it. That's how a hash table works. If the hash function behaves reasonably well, then the elements are going to be uniformly distributed across the bucket array. But many times, in fact, we will see that most of the time, you will have collisions where elements, 2 or more elements, are mapped into the same bucket. In the example, you can see, oh, sorry. How do I switch the, okay. Oh, it's so tiny that I can barely see it. Here you see that you have a collision. There's 2 elements that are mapped into the same bucket. So what is perfect hashing about? So perfect hashing is the happy circumstance where you don't have any collision. So in the example above, you see that all the elements are mapped into buckets that are not occupied by any other element. And minimal perfect hashing is the even happier circumstance where the number of elements is exactly the same as the number of buckets, where the load factor is 1. So all the buckets have 1 and exactly 1 element. This is minimal perfect hashing. How cool is that? This is cool, if we can get it. So you may have the intuition that you really need to be lucky in order to have a hash function that produces no collisions. In fact, you need to be extremely lucky. If we have n elements and m buckets, this is a formula that basically gives you the probability that a randomly selected hash function produces no collision or is collision free. Okay, let's analyze a little bit what the formula tells us about the behavior of this thing. If m, the number of buckets, tends to infinity, or in other words, if your bucket array is huge, then the probability that the hash function produces no collisions is basically 1, because you are mapping very few elements into a very large array, but this is not practical. We can have a tighter bound if the number of buckets is the number of elements squared. Then you have a 50-50 chance that the hash function will produce no collisions. So if you have, let's say, 10 elements and the bucket array has a size of 100, then approximately 1 out of 2 hash functions will be collision free. So this is not guaranteed, which is not a good thing. And the thing becomes, again, impractical, because if you have 1,000 elements and you need to have a bucket array of 1 million in size, again, this is just a curiosity, except if you have very, very few elements. And if we see how this probability function or formula works, when you fix the load factor, the number of elements divided by the number of buckets to 1, which is the case for minimal perfect hashing, you can see that the probability decreases exponentially to 0 very rapidly as n grows. And the graph shows the same behavior for different values of a fixed load factor as n grows. And you can basically see that the thing tends to 0 very rapidly, which is like obvious. There's this birthday paradox that basically tells you that if you have a hash function, you're going to have collisions. So the answer to the original question of how lucky must you be in order to get perfect hashing, extremely lucky. You have to be like the luckiest person in the history of the universe. So the moral of this story is that perfect hashing is impossible, and this concludes my talk. So thank you very much. No, we are missing something. I mean, there's going to be a way to have perfect hashing, and I'm going to reveal the trick or the missing information in the next slide. Little digression, this very beautiful sculpture is by an artist, Chinese artist called Ai Weiwei. It's on permanent display on the Elga de Alvear Museum in my hometown, Cáceres. So next time you go to Cáceres, don't forget to pay a visit to the museum, or maybe drop me a line and we can have a conversation while we visit the museum about C++ and art, etc. So what's the trick behind perfect hashing? When you have a regular hash table, regular unordered map or whatever, you select the hash function before trying to insert or delete elements. So you construct the hash table and then you begin to insert and delete elements, and that's basically it. Okay, so as we have already seen, the chances that the hash function is going to produce a perfect hash are 0. The trick with perfect hashing is that we require that the input elements are known in advance before selecting the hash function. So we have a probability, or we have a chance to try to be smart enough when selecting the hash function or the overall data structure that produces no collision. So this is the trick about perfect hashing. Perfect hashing is about knowing the input elements in advance and then trying to construct a hash table that has no collisions. There's two general approaches to try to create a perfect hash table. One of them is based on what is called in the literature universal hash functions. So basically, the algorithm or the approach assumes that you have infinitely many hash functions, and you can try and select many of them in order to try to combine them in a way that produces no collisions. And the other approach, or general approach to perfect hashing, is to create a hash function that is specifically designed and crafted for the input set at hand. So you're going to be examining the input set and determining how you can construct a hash function that works perfectly for that input set, because for the rest of the elements, or the rest of potential keys, you don't really care. I mean, whatever hash values produced is okay. You only care about making sure that for these input sets, the hash function is going to produce different hash values. All right. So what are the pros, the advantages, and the drawbacks of perfect hash tables? The advantages are about speed. You are guaranteed to have a constant time lookup because you're not going to have any collision. In the case of a hash table, you know, in pathological cases, you're going to have even linear behavior. Okay, this is not going to happen. This is constant time, and it is extremely fast at that because the resulting code has less branches. Okay, and for instance, in the case of minimal perfect hashing, you are going to have even less branches because you don't have to check for occupancy of a bucket. The bucket is already occupied. I mean, because you have a load factor of 1 and each bucket has exactly 1 element, etc. So there's a lot of opportunities for writing extremely performant code for a lookup. All right, so this is the biggest advantage of perfect hashing, but it comes with many drawbacks as well. For one, the table is immutable. As we have already seen, once you have inserted all the elements into the table, you cannot insert any more elements. So the use case is exactly that. If I know the elements in advance, I can try to construct a perfect hash table. Otherwise, you have to resort to a regular container. And construction time is going to be longer. So it is much easier to insert n elements into an unordered map than to insert them into a perfect unordered map, if you wish. So you have to take that into account. And there's also situations where the construction of a table can fail, because theoretically you can fail. I mean, there can be situations where you can't find the perfect hash function. This is a sort of equivalent to the case where you hit pathological behavior with a badly behaved hash function in a regular hash table. You're going to have linear lookup, etc. So the equivalent for perfect hash tables is that the construction procedure gives up and fails. So the takeaway from this slide is that perfect hash table is no substitute for regular hash tables. It is okay and very interesting for a reduced space of use cases where you know the keys in advance and you are willing to cope with the drawbacks that come from adopting a perfect hash table. How fast are perfect hash tables as compared with regular hash tables? I don't want to focus on the figure, on the exact numbers too much, but the blue line is the relative performance of a proof of concept perfect hash table that I will be talking about later on, as compared to Boost unordered set, which is a rather quite fast regular hash sets. And this is for integers and for strings, for different combinations of successful and unsuccessful lookups. Again, I don't want to focus too much on the exact numbers, but the performance can be anywhere from twice as fast to 4, 5, or 6 times faster, all right? So let's, this is a hard part of a presentation. Let's talk about some popular algorithms for constructing hash tables. We will review them lightly. I don't want to go into much detail, but I want to have a taste of what kind of techniques are used for this. The first algorithm that we're going to be describing, one of the most popular in the literature, one of the first to appear in the literature, is called FKS, for the initials of 3 Hungarian guys that designed it back in 1986, if I remember well. And the procedure goes as follows. You have your input set, in this case 12 elements, and you begin by mapping it into a regular hash table using some hash functions. So this is what we call the primary hash table. In this case, note that I have a load factor that is even higher than 1. So I'm going to have collisions for sure. Okay, so this is a resulting primary hash map, and then what I do is, for each bucket, I associate a secondary hash map, and I go and map the elements of these buckets into this secondary hash map. But the trick or the twist here is that the size of the secondary hash map is the number of elements in the original bucket squared. And if you remembered, when I have a bucket array that is the square in size of the number of elements, then I have a 50-50 chance that a hash function will work without collision. So I only have to try a number of hash functions until I hit the jackpot and I got this secondary hash table without collisions. Okay, so for that I need this universal hash function. I need to have many hash functions to try on. All right, so this is how the thing works. And the beauty of it is that we have produced a hash table without collisions, but the number of buckets is really very restricted. It grows linearly with the number of elements. So I'm not hitting this quadratic formula that we were talking about earlier. I don't need to allocate as many as n squared buckets, but only, well, the formula says that around 3n buckets is going to be enough. So this is undeniably beautiful, in my humble opinion. And let's move on to the second algorithm, which is like a refinement of the first one, called HDC, for hash displace and compress. I put the compress part in parentheses because we're not going to be talking about that part. This is important for some use cases of perfect hash tables where you need to compress the entire data structure when you are dealing with very large data sets, etc. And we are not going to be talking about that. So let's focus on the hash and display thing. So the algorithm begins exactly as before. We map the elements into a primary hash table, and then instead of allocating many different secondary hash tables or bucket arrays, I just create one with as many buckets as I wish. In this example, I kept the load factor to 1. It can be a little larger than that. That's it. And what I do is I try to map all the elements in the buckets of the primary bucket array using a randomly selected hash function and the displacement. Okay, and then I try to put all the elements there, and when I succeed, that's done. But the intuition is that there's no way I can succeed with that, because we have already seen what the probability of getting things right by random is. It's basically zero. The trick here, and this is again very beautiful, is that if I begin by mapping the buckets with the most elements and then I go in descending order, the procedure is guaranteed to work within some limit, some confidence probability intervals, etc. Why? Because when we are mapping the bucket with the most elements, the secondary, the final bucket array is basically empty, so it is very easy to do that. And as the bucket grows increasingly fuller, the number of elements that I need to map are fewer and fewer. When I get to the buckets with just one element, then I'm guaranteed to succeed, because I just need to select the displacement that basically goes and fills up the remaining bits of a bucket array. So if you don't believe me, you have a reason to not believe me, go to the paper. There's a theorem that proving that this actually works. And in fact, this is used by libraries that we are going to be reviewing. The final algorithm that I want to review is what I call, for want of a better name, because I didn't find any specific name in the literature, minimal cover. So suppose our key elements are numbers, 12 numbers like those in the slide. And this is the representation of the numbers in binary format. You see there. Okay. So if I'm able to come up with the number of columns so that the numbers filtered out to these columns alone produce distinct values for all the elements, then I have my hash function, because I only need to allocate a bucket array with as many elements as 2 to the power of the number of columns, and then I use this number as an index to the bucket array. How cool is that? This is also very cool. There's a problem with that. Problem is that the minimal cover problem is NP hard, which means that an exact algorithm is basically impracticable. Most implementations of this algorithm basically use an approximation which is linear time and very easy, basically trivial to write, and gives good enough solutions, okay? But the exact solution, you're not gonna get it. And another problem with that is that if you add another column, or if you require another column, the bucket array grows by 2. So it is very dependent on how minimal this minimal cover is. But otherwise, the whole thing is trivial to implement. On lookup, you only need to retain the mask or the columns that are important, and then you get the number, use the mask, compress the resulting, the filtered out bits, and go to the bucket array. There's a CPU instruction in x86 called pxt that does exactly that. So this is very, very fast. We will see how fast it is. All right. So these are the algorithms that I wanted to review with you. And there's another thing that you have to consider when constructing a perfect hash table, when to construct it. There's 3 points in time when you may wish to construct the table. I call them pre-processing time, compile time, runtime. What is pre-processing time? Pre-processing time is when you have an external tool, a program, we will see one of those, that takes the input set and generates source code specifically generated for implementing this very hash table. Then you use the tool, generate the source code, and compile or use or include the source code into your project, and you're good to go. All right. Then there's compile time, which is trying to do the same thing, but at compile time, typically using const expert magic, all right? And runtime, which works as a regular hash table, where basically you are providing the data at runtime, constructing the table at runtime, etc. So all of these approaches have pros and cons. Pre-processing time this is a bit messy because you need to include a generation tool in your build chain, etc. But on the other hand, it's typically very fast. It doesn't require you to have the latest C++ standard. So it comes with some advantages, some disadvantages. Compile time, it's going to require later C++ standards because, as you know, const export capabilities having like upgrading in the latest standards, and it's going to take more to compile because it's C++, you know. And as for runtime, sometimes it is the only option because if you don't know, even though you have to know the input set before constructing the table, it might be the case that you don't know the values before compiling the program because those values may be like acquired at runtime. Sometimes this is the only option. And even if it is not the only option, it also has some advantages, like typically you won't require the newest or the latest C++ standards because this is not so const export intensive. Compilation times are going to be okay. Well, you have, again, some pros and some cons. And the libraries that we are going to be reviewing, some of them are pre-processing time, some of them are compile time, some of them are runtime. We will begin with gperf, which is like the golden standard for perfect hash, or the baseline if you wish. This was written in 1989 by Douglas Smith, who is also famous for for writing a networking library called ACE. Maybe some of you are familiar with ACE, so those with silver on your hair will probably know about that library. Well, the guy invented also gperf. This is a pre-processing tool. You feed the tool a specification or a description of the keywords or the strings that are going to go into this perfect hash set generator, and the tool produces the C or C++ code for you. All right. The only container that this produces is a set, so no key to value map, so only a set for strings. So this is heavily oriented towards implementing like these type of functions that determine whether a given string is a valid identifier of a language or belongs to, I don't know, some set of HTML entities, this kind of stuff. And in fact, GCC uses gperf in some places exactly for that purpose, to identify C++ keywords in source code, etc. All right. The algorithm that they use is sort of minimal coverage, so it goes in the same spirit as a minimal cover thing that we described. And you can see here the generated code for a hash table of 100 elements, right? It's truncated otherwise. So it creates this class perfect hash with a hash function and in-word set functions that tells you whether the string belongs to the set or does not belong to the set. And the hash function tries to minimize the number of positions in the string that are inspected. So it is like a minimal cover thing. It makes sure that by inspecting only these positions, it can create a distinct value for each element in the input set. It does so by going through the position, from the positions through an indirection matrix called ASSO values that map into this word list bucket array, where you can see that the thing is not minimal, because even though we have most of the buckets are occupied, we have empty buckets. So the algorithm is not minimal perfect hashing. It doesn't have to be. And this is it. So this is how the thing works. And it works very well. Another library that I want to comment about is called Frozen. This was written or is being maintained also by Serge Geldon and some other guys. It is a compile time library requiring C++14, and it provides sets and maps that look more or less like your regular unordered sets and unordered maps. When you are constructing the thing at compile time, typically you will need to increase the number of const export operations allowed by the compiler, because the limit is going to be hit very, very early on. As long as you have 10, 12, 20 elements, you're going to hit that threshold, so you need to increase it, all right? And it works off the shelf for any key type as long as you provide a hash function for that. It provides off-the-shelf support for or hash functions for integral types and for frozen strings, which are basically string views. They are providing this for compatibility reasons because string views only appeared in C++17, but other than that, they are basically string views, all right? And the algorithm they use is the one we reviewed before called HDC. So they use a variation of that. And for the universal hash function, they take a hash function that accepts a value and a seed, all right? So by changing the seed, they are able to generate as many hash functions as they require. So this is how the thing works, all right? MPH is another interesting library. I'm including this in this library in this review for two reasons. One of them is the author, Chris Josiek, is with us. Where's Chris? Hi, Chris. So if I'm saying something wrong, he can correct me. And the other reason is because the library makes some interesting design decisions that makes it stand apart from the rest of our libraries that we are going to see in this talk, okay? So this is a compile time library requiring C++20. Again, you need to increase the const export operations threshold limit. And instead of providing a container, what this library generates is a function that accepts a key value and returns a mapped value, which at the end of the day, it's basically the same thing, all right? So it only supports integral types and strings capped in size to 8. In return, it is very fast, and it supports a variety of algorithms. The most interesting one, in my humble opinion, is the last one, which is basically a minimal cover variation using text, all right? So we will see how the thing performs. Other than that, it also has some other variations for corner cases or for some specialized cases, etc. What about Boost? Well, we don't have a perfect hash container yet. I'm working on trying to understand whether we should have it or not. In the meantime, I have produced a proof of concept thing called Perfect set, which is C++11. It is runtime, not compile time. There are advantages to writing a runtime only thing because I can use dynamic memory allocation, which I cannot use at compile time, all right? And it uses HEC. The main difference with respect to Frozen is that they used a universal hash function where they provided different seeds in order to have different values. If you remember, what we are doing here is we are hashing the elements just once, and we use the low bits of the hash value for the primary hash table and the high bits for the secondary hash table. So we try to minimize the number of times we calculate a hash value for an element in order to be faster. Other than that, it works basically the same way as Frozen does. And I also have a const export friendly version of that. This is proof of concept. I only written the thing in order to understand better how the thing works. Later during the year, I hope I will be able to make it into a real contribution to Boost. So if we measure creation times for these tables, and by creation time, I mean different things. For gperf, this is the time taken to invoke the tool and then compile the source code generated by the tool. For const export containers, it is the time taken to compile the source code where the container is defined. And for runtime containers, it is the time required to compile and initialize or create the table, all right? So gperf is very good. It stays like below 1 second for the numbers of elements up to 2000s. And the rest varies, all right? So MPH crashes at 100 elements, and we will see why this is so. Basically because it is, in my opinion, it is not designed to handle that many elements. And the rest, well, the Frozen at runtime, for a reason I cannot explain, it also fails at 1000 elements. And Frozen at compile time, this is the red line, has a very bad performance as n grows. And this is not due to anything intrinsical, it is a bug in Frozen. I will have to report that back. They are using a quicksort algorithm that behaves very poorly when the bucket array is mostly empty. And this is the reason why we have these spikes. This is when the bucket array grows to the next power of 2. And well, if the bug is fixed, then the performance of creating a table with Frozen gets very reasonable. For a lookup, again, I don't want to focus too much on the figures because the figures you get depend pretty much on your specific scenario. But in order to have an idea of orders of magnitude of how well things perform, this is the performance for lookup and for 100 elements and 1000 elements and different combinations of successful and unsuccessful lookups using HTML entities as the keys of the set. And this is gperf, Frozen, MPH, etc. For MPH, I needed to reduce the set, the number of elements to 60 because otherwise the thing crashed. And I also needed by design to cap the string length to 8 because this is the maximum that the library will take. So the comparison is not fair, but other than that, it is very fast. Okay, and the rest, well, some are faster, some are slower. This is how the thing goes. These lookup times, in any case, are going to be much faster than if you're using a regular hash table, that's for sure. There are some challenges associated to constructing a container, any container at compile time, and it also applies for perfect hash tables. You can basically, there's two ways of designing the interface for these type of containers. One, where the type of the table depends on the type of the elements and the number of elements. You need to have the number of elements when you are constructing the compile time container, all right? And the other one is when the type of the container depends on the entirety of the input set, of all the different keys of the input set. So this is like this, a second approach. MPH takes a second approach, which is this is one of the reasons I selected. Okay, so it has each design or each interface decision has pros and cons. Okay, one is probably enough for approaches based on universal hash functions, but when you're using engineered hash functions like with minimal cover, etc., it probably makes more sense to have the interface number 2. But then you need so-called structural strings. You need the regular string or string views cannot be used as non-type template parameters of your container. So you need to have a special string-like object in order to codify the input set there. And then the length of the resulting symbol is going to be huge. So this is the reason why you cannot go past 100 elements or a few dozen elements, all right? And there's also a problem with const export, which is intrinsic to the way const export is defined when the size or the footprint of your container. By footprint, I mean not only the size, but the data structures, the size of the data structures associated to the container. When this is a function of the size of the input, this is a function of n, you don't have any problem. But when the size depends on the input itself, for instance, for some inputs, I may need a larger table, and for some other inputs, I may need a smaller table, then the way const export works requires you that you perform the calculations associated to the data structure twice. Once for getting the size, then you need to allocate a static std array or something, and the second time you go and fill out or populate the data structure. And there's no way out of it. You need to do it that way, which is a pain in the ass, if you ask me. I'm going to skip this presentation, and the last part of a presentation will focus on some of the use cases that are good for perfect hashing. Okay, we have already seen some of them. Like this is the first one, translation tables or keyword detection. This is like the typical use case for perfect hash tables. You need you have some keywords or some a set of strings that you know in advance, and you want to be as fast as possible in determining whether some input string belongs in the set or not. Okay. Some other case is when you update the table very seldom, like you create it and maybe update it once or twice more, but you read many times. A typical use case for that would be JSON objects, where you are like getting the JSON object for, I don't know, from some file, okay, and then you are consulting the JSON object many times over, okay. So that would be a very good case for perfect hashing. Another one that we saw yesterday, the library jump2 from Jean-Louis Leroy, he uses perfect hashing for a dispatch table for virtual methods, etc. So this dispatch table is created just once at the beginning of the program, or maybe twice if a dynamic library is loaded, but other than that it remains fixed. So it makes sense to have a perfect hash in order to accelerate lookup as much as possible there, okay? Another use case is faster switches, and we are going to focus on that one to finish the talk. And another use case that we won't be talking about is database indexing. We won't talk about that because that requires the compressing part that we talked about earlier when we are dealing with input sets that are millions or tens or hundreds of millions of elements, okay? So this is a little out of scope for this talk. So let's see a bit how we can improve our switch statements, okay? So this is an example where I have a function that takes an input value x that may range, well, may take any value, but if the value is between 0 and 4, then we are doing some operation on an external variable y. So if x is 0, then y is multiplied by 2. If 1, we added 7, and so on and so forth, okay? So you can see the assembly there, and this code is very good because it only has 2 branches. This is to determine that x is between 0 and 4, and this is a jump table where, depending on the value of x, we execute the associated action, and these are the actions. So this is very easy to read, okay? What about if instead of having these very nicely consecutive values, we spread them a little bit? Okay, so instead of 0, 1, 2, 3, 4, we have these values. Then again, the compiler determines or thinks that it is worth keeping the jump table approach, and it basically expands the jump table and inserts do nothing operations for the cases that are not covered in the switch, like 1 or 4, 5, 6, etc. Okay, but if we keep making the values more sparse, then the compiler gives up, and in this case it decides that the jump table is not effective anymore, and it's basically doing a binary search on the different values of x. So it begins by comparing it with 31. If it is less than 32, if it is less than 32, then it goes to that part, otherwise it goes to that part. So this has as many as 4 branches. Can we do better than that? Yeah, we can use perfect hashing to do better than that. Like here. So this is like a very tiny minimal perfect hash table that maps the values that you saw before, 10, 21, 32, etc., to values 0, 1, 2, 3, 4, and 5, meaning that the value is not in the set. All right? And instead of doing the switch on x, we do the switch on the perfect hash function of x. So the switch is 0, 1, the cases for the switch are 0 to 5. Anything other than 5 is unreachable, and we can tell the compiler that it is unreachable, and the compiler will take advantage of that information. And the resulting code has only 2 branches. Okay? How cool is that? Well, you have to be very careful. As soon as you begin to do these micro optimizations, if you change one tiny bit, then the whole thing may be like ruined, etc. But it shows that perfect hashing for these micro use cases can make sense as well. All right? What about strings? As you know, you cannot have a switch on strings. So if the input value, instead of being integer values, are strings, then the only thing you can do is to do a sequence of if checks. Okay, this is the resulting code, and the compiler is very smart because it determines that all the checked against strings have size 1, and it verifies that the input value has size 1 before If it is something, if the length is something other than 1, then we are done. There's no action to be taken. And if the input value has a size of 1, then the comparison with the different values is done only on this very chart. So even though this is not optimal, or we can do better, the compiler is being extremely wise, extremely smart here, all right? How can we do better? We can convert it into real switch by having this perfect hash function that basically does the same thing as before with the numbers. When the strings are 0 to 4, it returns an integer value 0 to 4, and otherwise it returns 5. Well, not 5. In this case, this is not, it can return anything other than 5 as well, okay? And the resulting switch is like this, and we have gone from as many as 6 branches in the worst case to 3 branches in the average case here, all right? So this is a nice application of perfect hashing. So conclusions. So the key insights and the thing to take away from this perfect hash talk is that perfect hash is not a replacement for regular hash. It is something that you can try in order to speed up your lookups when you know the key elements in advance. If you know them, then you may try it because you are in a very performance critical scenario or something like that. There's 2 algorithms or like wide approaches to perfect hashing based on universal hash functions or on engineered hash functions, and the tool that you are going to use may follow 3 different approaches as to whether it has to be used at pre-processing time or compile time or run time. Gperf is a really good tool, even though it is very, very old. I think it is very hard to beat it, okay? And const-export construction of perfect hash tables and containers in general is still subpar. I mean, there's some limitations to const-export that make it a little hard to do this kind of thing. One of them is that we cannot allocate dynamic memory in const export. In other words, we can do it, but when the const export function has finished, all the memory allocated has to be released, all right? There are some papers being discussed on the committee in order to increase the capabilities of const export so that non-transient or transient, well, persistent memory, dynamic memory allocation can be done. And that would be very, very useful for the creation of compile time data structures. And we are going on with our investigations on whether we should produce or provide a perfect hash container for Boost. So if you're interested in that conversation, join us at cpplang.slack.com. And that's basically it. I want it. Thank you.
So, questions?
Thank you for the talk. I was wondering about the use case where you have the runtime and you try to use universal hash functions. In that case, do you also have to code for the fallback scenario that it fails to create? And you have to program with regular hash tables?
Fallback case?
In case that the hash function is not able to find a unique...
I don't think so. I mean, the problem with providing a fallback case is that it's going to impact the lookup performance for the regular case because you have to check whether I'm on the fallback case or I'm not, okay? So in all the situations that I have seen, you basically assume that the thing is going to work, and otherwise you throw an exception. That's a problem. But it is not a bigger problem than having a pathological hash function in a regular hash container. Because even though you're not going to get an exception, your lookup time is going to be so awful that your program is going to stall. So you have to consider whether, I mean, there's some intuition or some like gut feeling that this is preferable to throw in an exception because I wasn't able to create a hash table. But if you think about it rationally, I'm not so sure what's worse.
Okay, thank you very much.
You're welcome.
More questions? Looks like people want coffee.
Yeah.
Thank you.